Hi everyone, we are Synchro-Sense, enabling doctors to make better treatment decisions for ventilated patients. The team is comprised of Justin, Ruby, and myself. To begin the presentation, we will talk about the unmet need for our device and then progress to the overview, data and testing, and then future steps. First, I will give some brief background information essential to explaining our device. Breathing is essential to get oxygen into the body and expel carbon dioxide. The lungs normally perform this function by expanding and drawing in air and then contracting and expelling it. Mechanical ventilation is required when a patient needs assistance with breathing or the patient's respiration needs to be mechanically maintained. The patient is connected to the ventilator with a hollow tube that goes into their mouth and down into their main airway or trachea. Common conditions that cause a patient to go on a ventilator are severe heart disease, acute lung injuries, sepsis, and viral infections. Now, it is important for us to look at the ventilator landscape to put our product into perspective. Approximately 800,000 patients go on ventilators each year in the US alone. This could be a low estimate due to the increase in ventilation due to COVID. Some figures suggest that it might have been as high as 1 million people last year. The mortality rate for ventilated patients is approximately 35%. This is obviously extremely high and a space we need to improve upon. And lastly, roughly 5% of symptomatic COVID patients have to go on a ventilator. Now, the problem is when you get a chest x-ray, the x-ray technician tells you, take a deep breath and hold it. But patients on ventilators are unconscious and therefore cannot be instructed. This leads to a lack of synchronization between images. As you can see here, there's a huge difference between lung size between an image of the same lung when at full inhalation versus at full exhalation. According to the NIH, lung volumes can vary up to 15% over the course of the breath. This demonstrates the critical need to get images at the same time in the breathing cycle so patient decisions can be made on using the most accurate info. Patients on ventilators must be x-ray imaged at least once a day, and these images are critical for patient care and treatment decisions. But lack of synchronization between image capture and inhalation leads to over-medication and unnecessary treatment. Doctors can unnecessarily prescribe bronchodilators, corticosteroids, and methylxanthines, all of which are drugs to assist breathing. Also, when images aren't taken at the right time, patients have to be re-imaged, which can lead to unnecessary extra radiation. We do not want to let a simple problem such as this get in the way of patient care. Now I will hand it off to Ruby to discuss the goals of Synchro-Sense.
Thank you, Raina. The goal of Synchro-Sense is to detect when the patient is at maximum inhalation to trigger the X-ray image to be taken. This allows for consistency across all X-ray images taken for a patient, which leads to doctors making better treatment decisions for their patients since they have the most accurate imaging information. This also helps to minimize X-ray radiation for the patient. There is currently nothing on the market right now to address this problem, and it is up to the individual timing of the X-ray technician, who will usually have to retake images. Now we will talk more about the details of the Synchro-Sense device. The two main components of Synchro-Sense are the adjustable strap with the tension sensor and the device enclosure. The strap consists of a nylon band with a flexible tension sensor attached by Velcro strips. The central device consists of an LCD screen to alert the X-ray technician, a power switch, and a red push button to initiate the training period. Now I will hand it off to Justin to talk more about the design process.
These three images show the progress we have made on Synchro-Sense since the beginning of the last semester. On the very left, we have our proof of concept design, and as you can see, the wires and circuit components are exposed, making this design fragile. The strap is also thick, which is not ideal because we want the X-ray image to be obstructed as little as possible. We were able to improve the durability of our design in our minimum viable product by enclosing our device in laser-cut PVC, and we also made the strap thinner. However, the box and the sensor are still connected by wires, meaning the X-ray technician would need to be right next to the patient to use our device. This is not ideal since the technician still has to operate the X-ray machine from a computer, which is often on the other side of the room. In our final design, we fixed this logistical issue by adding Bluetooth functionality to our device so that the sensor can communicate with the device wirelessly. We also 3D printed a new, more aesthetically streamlined enclosure and included a pouch to enclose the circuitry of the sensor. To further reduce image obstruction by the sensor, We replaced the metal sensor with the more durable, conductive rubber sensor so that it will not show up in the image. To allow our device to be battery-powered, we also installed power switches on both components of our device. Finally, we replaced the push button and LCD screen with higher quality components. We use MKR Wi-Fi 1010s for our microcontrollers to allow for wireless capability via Bluetooth Low Energy, or BLE, between the device and the strap. BLE uses Universally Unique Identifiers, or UUIDs, to facilitate communication. The UUIDs are used as handles to send and receive information between the components of our device. The peripheral component, which is the sensor, broadcasts data, and the central component, which is the main device, receives and processes the data. We use randomly generated UUIDs so that no unauthorized devices can connect to either component of Synchro-Sense, which is crucial considering the importance of confidentiality in clinical settings.
There are several specifications that our device aims to achieve. For one, we aim to minimize the delay time to capture the X-ray image within 15% of the patient's maximum inhalation. Our device also needs to be adjustable to accommodate different patient sizes and be portable and compact, weighing under 10 pounds. Lastly, our device needs to be easy to use with a substantial battery life, easy to put on an unconscious patient, and a user-friendly design requiring minimal training. The major costs of our device have been categorized into hardware and electronic components, parts to build the adjustable strap, and general materials to complete the device. Given its practical and portable design, our device is low cost and suitable for settings with minimal resources. Now I will hand this off to Justin, who will talk through a demonstration of our device.
This video demonstrates how Synchro-Sense is used. As you can see, we've pressed the button to begin our calibration period of 10 seconds. Over these 10 seconds, the maximum tension value is stored, and then once the 10 seconds have elapsed, it waits until the maximum tension is reached again. And as you can see, the image was captured at our patient's maximum inhalation. Now that we've explained how the most important parts of our device work, I will discuss the testing of our device. We were incredibly fortunate to be able to test our device in a clinical setting thanks to facilitation by our clinical mentors at CHOP. We decided to test our device in real time alongside a device for electrical impedance tomography. EIT is a non-invasive type of medical imaging in which the electrical conductivity, permittivity, and impedance of a part of the body is inferred from surface electrode measurements and used to form a tomographic image of that part. To quantify the error in our device, we used video analysis to find the difference in time between when Synchro-Sense determined maximum inhalation and the actual top of the waveform from EIT. We then used the tidal rate from EIT to find the length of one breath cycle and found the error in percent lung capacity using the difference in time. Finally, we subtracted the error in percent lung capacity from 100% to find the lung capacity at the time that Synchro-Sense determined maximum inhalation. Here's an example of our validation testing. You can see the waveform on the EIT screen as well as the collected data from Synchro-Sense on the serial monitor. In the top right of the EIT screen, you can see the tidal rate. These are the results of our validation testing for 10 trials. The mean lung capacity at the time of image capture from Synchro-Sense was 86.96%. The bounds of the 95% confidence interval were 88.38% and 85.54%. This means that even when accounting for our 95% confidence interval, we meet our specification of at least 85% lung capacity at image capture. We can further improve these numbers in the future by raising the threshold tension value from the sensor in our algorithm, causing our device to wait for tension values that are even closer to the maximum before image capture.
Thank you, Justin. Now we will describe future steps for Synchro-Sense. Since our last presentation, we have continued to enhance our design through the LCD screen, an improved tension sensor, and a new strap. On April 9th, we performed our validation testing with the help of our CHOP mentors. We are currently continuing to update our device to reflect the information we gathered during validation. After graduation, we will plan to continue working with our mentors to ensure that the device will be useful in the clinical setting. We would like to give special thanks to our mentors at CHOP, Natalie Napolitano, and Dr. Dave Munson. We would also like to thank the Stevenson Foundation Bioengineering Lab and the lab staff, as well as our technical mentor, Mike Seidlich. We would also like to thank Pam Batrice and Deneen Wambach from the Penn Center for Innovation. Thank you for listening.